So how many of you have done the course on biological networks? That's online based elective? Nobody. So then this is going to be new to you, which is good. Okay, so let's get started. I'll just give you a quick introduction to networks. I put biological networks, but I think it's a very generic introduction to networks, the concept of networks and graph theory itself. So it's always good to start with the history of every field, so you understand really how things evolved in that field and what actually led to the creation of this really exciting field. So this is very nice. So this is a problem set in the Prussian city. It's presently in Russia, called Königsberg in 1735. And the city's residents had a question. So what you see is like a map of the city, and they had a question: if can I set out from my house in any of these places? There are so many bridges here. You can see 7 bridges if you really strain your eyes. So can I cross all these bridges exactly once and get back home? Seems like a very silly or simple problem, and but those days I think people had lots of fun in life. So they wrote a letter to the mayor of the city saying, is this possible? And the mayor in turn wrote to Euler. So I always say that any field of mathematics, you cannot start it without paying your respects to Euler. He has touched the maximum number of fields that you can imagine, and really fantastic at that too. So his solution to the problem laid the foundation to graph theory. So what did Euler do? He wrote this really nicely worded letter. Thus you see, most noble sir, he's writing to the mayor, how this type of solution bears little relationship to mathematics. Mathematicians will be really aggrieved to see this. Right? He says graph theory has nothing to do with mathematics. And I don't understand why you expect a mathematician to produce it rather than anyone else. For the solution is based on reason alone. And his discovery does not depend on any known mathematical principle. And very nicely he says, I don't know why questions which are not connected to math are also better solved by mathematicians. He's basically saying that mathematicians are really smart, which is true. But the interesting part is this really, which is what is gave birth to the field of graph theory. So the question was very banal, but seemed worthy of attention in that just geometry or algebra or the art of counting was not sufficient to solve it. So Euler himself had to develop some new math to solve this problem. What did he do? He actually didn't draw this. We draw it like this today. But this was Euler's caricature of the city. And what he showed was that there is no Eulerian circuit in this graph. Obviously, he didn't say that. He said that there is no path in the graph where you can start from the same place and come back to the same place. He didn't use the word node or edge and so on. But he showed that this is not possible. You cannot start from the blue node and come back to the blue node by going over every single edge. This is, you may remember something like this from school. Can you draw this figure without taking your hand off the paper? Right? So this is nothing but trying to find an Eulerian circuit in the graph. So anyway, that's like a very fun introduction, but that's the real history of graph theory. So any course in graph theory will actually start with this kind of an introduction to graph theory. What are graphs? A very, very important theme in computer science. Every graph is described by by 2 sets. A set of vertices and a set of edges. So G, V, E. So a graph G is given by V and E, where V is a set of vertices and E is a set of edges, and E essentially is a subset of V cross V. Has all pairs of vertices. And the interesting part is that there are various things, right? So this, so if A and B is in E, is B and A also in E, and things like that. So then it becomes a directed graph, undirected graph, and things like that. I'll just touch on some of those concepts. But what is most important is that you really get a hands-on experience to graph theory, which is why my students will help you with doing some of these simple analyses in NetworkX. Graphs are often referred to as networks as well. So road networks, social networks, metabolic networks, and so on. And they're also classified very elaborately, which influences what kind of algorithms you run on those graphs and things like that. So first classification of interest is what is a directed graph versus what is an undirected graph. So it's obvious from the picture that when you have these arrowheads, we'll say that there is a notion of you can go from A to B, but you may not be able to go from B to A. That is a notion of direction, okay? So an example is, Facebook is an undirected graph. You both are friends on Facebook, that's it. He's your friend, you're his friend, that's it. But Twitter, you may follow some celebrity, but they may not follow you back. So Twitter is a classic example of a directed graph, where the relationships need not necessarily be symmetric. So similarly, road networks, are they directed or undirected? Well, in India, the way people drive, it is undirected. Everybody will drive in every direction, but you honestly have one-way roads. So which means that if to go from this place to that place, you can take this road, but you cannot take the same road to come from that place to this place. But can you think of, this is where I want you to start thinking a little further, what about highway networks? Are they directed or undirected? You can argue it both ways, right? Leaving aside lawless people, what you can have is the same highway that connects Chennai to Bangalore will connect Bangalore to Chennai. But it's necessarily not the same road, right? It's the opposite set of roads. But as a model, you may want to just model, if you're just looking at connectivity between cities, you may not want to complicate the model by including direction and things like that. Because there is no other, unless you have a rare scenario where there is a complete accident and there's like a major renovation going on in one part of the highway. Even so, they will put some barricade and let people use the same highway on the other side, right? So the same set of roads essentially connect Chennai to Bangalore or Bangalore to Chennai. So this is what you will see, and this is where you start thinking about how to model the system. The reality might be something. The reality is you have two roads in opposite directions. I might simply represent it as a single edge without direction. We can go into all these details later on, right? So how will I represent this and so on. Similarly, airplane networks, are they directed or undirected? Airplane networks are even more challenging. Because you will have, the question will start becoming, what is it that you're actually trying to model? Are you trying to find the cheapest way to go from Chennai to Kolkata? Or are you trying to see if there is a connectivity between these two cities? Or what? So these are some of the questions you will start asking. And in a simple graph, you have only one edge between two nodes. Whereas if you're trying to model every flight as an edge, which is logical, right? Every flight connects one city to another. So you can think of cities as being the nodes in the graph and flights as being the edges in the graph. You'll have multi-edges, you'll have parallel edges, you'll have multiple flights between any two cities, typically. So you have to start thinking, how do I want to model this system? And that is a result of what is the question you want to answer with that system. You may have a very specific question. So if there is a shutdown of, say, Mumbai airport, which is a or Delhi airport, how do I reroute traffic so that the country doesn't come to a standstill? You can try to ask and answer these kinds of questions using graphs. And all of you have used weighted graphs. You may not know that you have used it, but all of you have used weighted graphs. I'm assuming all of you have used Google Maps. So Google Maps is a weighted pathfinding between two nodes on a graph. What is the graph? It is a road network. What is the node there? What is an edge? It's very easy. Road. Every road is an edge. What is a node? A place where multiple edges meet, multiple roads meet. Any place where multiple roads meet, what are they called? No, in English, in the context of roads, junctions. Every junction becomes a node and every road becomes an edge. And it is a directed graph. And it is a directed weighted graph. What is the weight? Distance possibly, but you rarely use distance, I think. Traffic is what you use. There is also something else which you may not use much. Cost, tolls. So these are all the options available to you on Google Maps. You can find the shortest path, cheapest path, fastest path. All these are weighted pathfinding problems on a graph. Okay? The one thing that's interesting is, of course, I don't know how many of you are interested in biological problems. In biology alone, the notion of an edge weight is slightly different. In biological problems, the notion of an edge weight is that it is typically a confidence. Whereas normally it is a cost. Can you imagine that cost and confidence are ulta? Cost is you want lesser traffic. Higher traffic is higher cost. Right? Higher time is higher cost. Higher money is higher cost. Higher tolls is higher cost. Whereas if I say I'm very, very confident that there is this edge that exists between these two proteins or two entities in a knowledge graph or something like that, that means that a high weight edge is actually good. So this is something that you need to keep in mind when you work with biological networks and so on. And typically it could be probabilities. You may have a score of 0.9, which means that these two edges are very, very likely to be connected based on the experimental evidence or whatever I have and so on. Whereas some edges may not be connected. They may have a very low confidence of say 0.1 or something like that. And then you have other kinds of graphs. You have labeled and unlabeled graphs, sparse versus dense graphs. They are possibly you can guess what they are, but let's not get into all the details. I want to give you a quick intro so that you can actually do meaningful hands-on stuff. There is the other concept which is very useful, which is that of a bipartite graph. I'll teach you two concepts here, which I think are fairly useful. There is this very interesting or funny game known as the Kevin Bacon game. This was invented by some college kids in the US. The idea is, how many of you have even heard of Kevin Bacon? He's an actor. At least somebody has heard of him. I never heard of him before. I only looked at him in this network science theory. So the idea is, how can you connect an actor to Kevin Bacon? Suppose you say Robert Downey Jr. You have to say the names of a few movies in which they starred. So Robert Downey starred in movie X with some person, and that person starred with Kevin Bacon in another movie, something like that. So you have to connect somebody to Kevin Bacon. This was the thing. So for this, what is the kind of graph one would use? So anytime I ask you what graph, you have to identify two things for me. What is a node? What is an edge? And maybe, in this context it's not important, what is the weight of an edge or something like that? What does it mean if two nodes are like tightly connected or loosely connected or whatever? So what would be a node and what would be an edge here if you are talking about movie actors? Actors are nodes and movies are edges. But there is a problem here. Suppose I say there is an edge between Robert Downey and Kevin Bacon and Amitabh Bachchan, whatever. Does it mean that they acted in the same movie together or they acted in 3 different movies? That information seems to be sort of lost. Are you getting my point? Suppose I say there is an edge between A and B, B and C, C and A. Does it mean they acted in 1 movie or they acted in 3 movies? You don't seem to know that from this representation. So I can give you a slightly more complex representation. Let's make everybody nodes. Movies, actors. What happens now? Can you think? So this is literally a membership network. A is a member of this movie. B is also a member of this movie. So I think we may need the lights, but let me try to do. And one thing you can do is you can have 2 different shapes here to distinguish very conveniently. I can represent actors by circles and movies like this. These two are very different. Can you see that? Assuming you can even see it. So can you see that these two are very different? What does this mean? Each of these two fellows acted in 2 different, in a single movie. Here all 3 acted in 1 movie. This is known as a bipartite graph. Why bipartite? The strict definition is that, it's actually a very cute definition. You can color the graph using 2 colors. I can use one blue chalk and yellow chalk to color the graph, such that no 2 adjacent nodes have the same color. But anyway, I've conveniently drawn it in 2 shapes. So you can see that. So there are no connections between movies and movies or actors and actors. So actors participate in movies, movies have actors. But then you can readily answer all the questions that you want with this network too. And very interestingly, you can create 2 projections of this network. What do I mean by a projection? I can create a movie actor network out of this, or I can create a movie network out of this. So take paths of length 2 and start connecting them. Is this connection there? No, I think it's not there. 1, 2, there is no path of length 2 unless these 2 fellows acted in another movie here. And here, I can connect these nodes. So I now have a movie network where the edges will tell you how many actors those 2 movies shared. Or I will have an actor-actor network which will tell you how many movies these two actors starred in. Of course, I don't think people really study movie actor network so much, but they study very similar networks. Let's say a very important network is co-authorship network. You have people writing papers. So what kind of people collaborate with each other? What kind of fields get cited by other fields? This is a very important network that is studied by various kinds of scientists, including social scientists. So this is like a quick intro to a few kinds of graphs. I'll not get into hypergraphs. If you know bipartite graphs, you can understand hypergraphs if you go and read it up on the internet. Okay, there's a lot of correspondence between the two. So why graph theory? You may have questions like, do I know someone who knows someone who knows someone who can get me a ticket to the IPL final, right? Or how long is that chain? Or is everyone in the world connected to everyone else? Who has the most number of friends? These are all questions the social science people ask. Are X and Y friends? When you log into some social network, it will pop up, no, is this person your friend? That's because it's doing an edge prediction, link prediction on that network. But watch the slide carefully. I'm just going to switch to biology. The algorithms are the same, only the questions slightly change. Is there a way to produce a particular drug from some other metabolite? How long is that sequence of paths from, sequence of reactions from one known molecule to a drug molecule? Are all proteins connected to each other and so on? What is the most influential protein? Do these two proteins interact? No, or is this drug going to inhibit that protein and be useful against fighting a particular disease? Whatever. But basically, many problems naturally map onto graphs. There are several graph algorithms like shortest path problem, traveling salesperson problem, finding strongly connected components, graph isomorphism. I'm not going to go into any of these things. But I'm just throwing a large list of algorithms to you so that you can go and look them up if you're interested. Maybe I'll just talk about something which I don't have on my slides, which is how many of you heard of PageRank? Handful of people. What is PageRank? Okay. Two? So what PageRank does is it essentially tries to rank pages. It's a nice wordplay. PageRank is called so because it was invented by Larry Page. Not because it ranks pages, but it's a beautiful pun. So the idea of this is it tries to figure out what is the most important node in a particular network based on certain characteristics. So this is what is known as a centrality measure. So there are certain nodes. So if you look at a road network, right, there will be some junctions which have lots of roads connected. Or some airports which have lots of flights, like those are the hub airports. So those are the ones which are very, if something goes wrong there, right, if there is like a shutdown or like a flooding of the runway or something like that, whole air traffic will come to a standstill. So these are things that you can study from network structure and so on. And PageRank, of course, is a $1 billion algorithm, right? It's what made Google so successful. But PageRank itself, if you see, is a very simple idea. In the sense, it's built on something known as eigenvector centrality. Maybe I'll not get in the details, but you can compute those things using NetworkX in the lab today. So I think this is really what I wanted to cover. I just wanted to give you a very hurried introduction to networks. You know what a network is. Now let's see how do we work with networks. And there are so many interesting applications for networks. So maybe I'll just quickly talk about some of those applications. So the applications you see are in so many different fields. It could be in drug design. It could be in trying to identify new drug targets. It could be in epidemiology. All of us have just thankfully come out of COVID. But how do you track the spread of the disease? You need to track it on social networks. There are, this person came into contact with this person at this time, so he or she could have passed on the infection from this location to the other location. So there are networks people constructed very similar to this, bipartite graphs, using people and locations. So this way you'll know where you can implement a lockdown, who should you vaccinate first, all these kinds of questions you can answer. Or airline networks, how do you find out the shortest way to travel from one place to another? Or how do you fortify airports? Which airport has to be most secure from, say, a terrorist attack? All these kinds of questions you can answer using network science. So hopefully you'll have a lot of fun tinkering with NetworkX. but I'm very happy to answer some questions you may have over the next few minutes. So you can map this back into any other concepts you've studied in the past, anything else. I'm happy to answer any questions that you may have. Yeah. So in fact, air traffic control have their own models, right? I mean, I'm not sure. So graph theory may not be the most important thing there, because they probably work on more queuing models and things like that. But definitely, it will help you answer certain questions at least. In fact, we wrote a paper some years back trying to show that how you can, if there is congestion in a particular airport, what are the flights you must create to reveal to sort of alleviate that congestion, and things like that. So all these are network science questions essentially. Yeah, so here I don't see like a full network there, right? So it's essentially like one set of things that connect. So instead, in fact, in the automotive industry, where this is used is in the supply chain. So there is this book called 6 Degrees by Duncan Watts. He has a full chapter on Toyota's just-in-time thing, where he talks about how the supply network is structured and things like that. So some of these are, can be captured using networks, but you may not see the full payoff for network science in that, because it's relatively small. Because so the challenge comes in when you have lots of hidden factors. So now let's say your seat belt itself, the performance of the seat belt or something like that, has like another 10 different factors that contribute to it. Right? And those some factors are also involved in, like, say, I don't know, I mean, I'm not an expert in this field, but let's say, there are some components of the window or the door. So it plugs into multiple factors. You can actually then start analyzing a network. So when the components become very large, when you have too many components involved, that's when you need the power of network science to navigate it. I think that makes a lot of sense. You can definitely try and apply it in that context. Essentially, when you, for example, you can find even like anti-correlations, right? Like, when this law is, this is applied, this is never applicable or something like that. You may be able to mine those kinds of things and so on. So I'm glad the way you're thinking, because I really believe, honestly, that network theory must be taught in schools. Because this is not too difficult. 11th standard kid can totally take this up, but you can start applying everybody. I think 7th standard kids start using Google Maps. So I think you really you need to have this sort of picture of how do you start modeling things, right? You know that you can use this is one hammer you have, but what is the nail you're going to hit it on? You have to figure out how to map. Like, so now you started saying, so this clause, that clause, things like that, and connect it with different kinds of cases, then start putting labels to that, and then see how often are these. In fact, people have, I didn't go into the application. So we have an application where we predicted essential genes in protein, in organisms, which you can target using drugs, solely based on their interaction network. And the interaction network, you computed several centrality values and did simple machine learning, all that. No fancy, not even, deep learning or any of those things. Just simple random forests, and we could make some very useful predictions. So I think these are very good ideas to try and work out. If you have a capstone project, you want to tinker around with this, we can talk about it. Yeah, any other questions? Absolutely. I think that's a very good point. Typically people use food webs. And this is a very similar, notionally similar to something like a food web, right? So because you have like items and species, right? So I think, I think that's again a very nice way to, so these are the ways to start thinking about this. So you can ask questions about what is is ocean microplastic the first problem you need to address? Or is it something else? Based on PageRank, for instance, right? That might be a very nice way to look at this problem really. And so many things you can start, so many layers you can start adding to this. So you'll see that, you'll start seeing everything as a network. And that's what it is, right? Everything is internetwork. Even the human body, right? You cannot treat one organ. It's a complete network, and the network has gone dysfunctional. If you're saying somebody has diabetes, it's not like one protein stopped functioning. You can say that, okay, pancreas is not producing enough insulin. But it's not just that. There is like a very complex network that has flopped somewhere. So you have to figure out where to hit in that network. So these are all biological networks. So it's a network of biological small molecules. It's a network of biological proteins. It's a full metabolic pathway where you have different types of nodes for enzymes and different types of nodes for small metabolites and so on. So the good part is that all this data is readily available for us. For lots of organisms, these kinds of models are readily available and so on. So you can actually start asking the questions you want to ask of these models. I wouldn't say that our knowledge is 100%, but in many organisms, we have excellent knowledge of what are all the enzymes, what are all the small molecules that are present and so on. And we can ask questions like, is it possible to produce something from this thing? What kind of new reactions are possible in this system? Many interesting questions can be asked. Great. Please feel free to reach out to me even later on if you have any questions. Yeah. So neuroscience and the neural networks is a huge field of its own. There are lots of people who have studied these kinds of networks and what kind of topologies are there, when these neurons will fire. All these things people are studying. So it's very possible to bring graph theory into those contexts as well. So feel free to write to me anytime. I'm more than happy to answer any queries you may have on graph theory, network science, or computational biology in general. So but I think now we'll switch over to the hands-on session, which I think promises to be a lot of fun. You can actually get your hands dirty trying to work on these storing graph objects and things like that.
So we have designed this hands-on session into two parts, wherein the first part we will introduce you guys to the NetworkX library, wherein we will cover the basic things that you would require to get started with. And then the second part is we have a few set of questions which are normal questions that we used to ask to within our friends or even to someone who's working in the say road network related authority. And then we will try to get the answers by using whatever we learned in NetworkX and then in network theory from the graph of road networks. Okay. So in order to start that, we would or others able to connect to the internet and access then we will get started. So others, once you guys are able to join, you can follow along. So NetworkX is an Python library. I assume you guys are pretty much well aware of Python and the basic libraries that are used in data science. So NumPy, Matplotlib for plotting and so on. So we'll be, again, NetworkX is a kind of a wrapper which uses the other packages which you guys use in your daily data science work, right? So if you know them to some extent, then NetworkX is pretty much simple. You just get new functionalities that you can use to query a network or do some calculations on top of that. So it's simple. So my job here is to just teach you how to get started with NetworkX. And then from then I will also show you the connections between NetworkX and then the libraries which you already know. And then we'll go through a few basic algorithms or basic techniques that you would be using to ask questions to a given network of your choice. So it's just simple. NetworkX is the name of the library. So you can import NetworkX as NX so that it's easy for you to call it in your code. And then so how do we create a graph? So it's very simple. nx.graph with G caps. So this is going to create us an undirected graph. So Sar, when he was in his presentation, he showed multiple types of graphs. So the first two things which are pretty much common is directed and undirected graph. So we'll also look into the directed and undirected graph here. But NetworkX has functionalities for other graphs also. Okay. So yeah, so graph nx.graph is going to create us an object G, which we can use to build an undirected graph. If you want to use a directed graph, there is another function for that. We'll get to that. And as I was saying, NetworkX offers a lot of different types of graphs are all those there. I will show you how do you browse it or how do you go into the NetworkX API and API documentation page and how will you be able to find it, right? So And then we got introduced to this concept of nodes and edges, right? So nodes are some entities and then edges are connection between those entities. So how do we add nodes in a network into a NetworkX object? So NetworkX by default has many ways in which you can do same or similar things. So I won't be going into all sorts of ways in which how you can add a node to a graph. So I'll just cover the basic things and then I will let you guys to explore the rest of the ways in which you can do the same in using NetworkX. So the simplest thing is just dot add node and then you give a name for that node. It could be a number, it could be a string, it could be a tuple, or basically an immutable object in Python can be used as a name for node. Any doubts so far? No. Cool. And then again, so this is like you are going to add it one by one. There is another way you can also pass in an iterator like a list or a tuple. So you just have to use this function. So add nodes from and then give an iterator. As I said, there are like multiple ways in which you can do the same thing in NetworkX. So these are like the common two ways that I thought you would like to know. And then when it comes to adding edges, you can add them one by one, as in here g dot add edge between 1 to 2. So 1 will be the source and target in a directed graph. In an undirected graph, there won't be any source and target, just an edge between 1 and 2. And then here also you can give a list of list, as in the same what we did for nodes. So add edges from and then a list of tuples which are comparing, which has a pair of nodes that we want to add here, right? And these are all other ways in which you can add. So again, you can add edges as a immutable list, immutable tuple. You can name them using strings also. And then if you use this add nodes from and then you give the string, it kind of creates as 4 nodes. So S, P, A, M instead of creating a single node called as spam and so on and so forth. Like multiple ways to play with it. And then the simplest thing that you would like to do with a network is, given a network, is to know how many number of nodes are there, how many number of edges are there. And there's a easy command for that, just numbers of edges and numbers of nodes. It will return how many numbers of nodes and edges are there. So those are the main thing that we want to do with an undirected graph. And then when it comes to directed graph, you have something, how do we initialize a directed graph? It's simple, di graph. Now we have a directed graph object. And then the edges will have directionality. So the first one will be the source node, and then the second one in the edge list will be a target node. So here there's a directed graph starting at 2 and then ending at 1. Same thing for every other thing. And then there are like these special functions, so to say, for directionality, a directional graph. So there is something called as successors, which in it lists the nodes which are in the tail side, so the target side of a given node. So what are the successors of node 2? Then it gives you the nodes 1 and 4, which are in the target, which can be reachable from source node 2. And then the normal one dot edges gives you a list of all the edges in which a particular node is involved. So if I put edges and then if I give 2, then it gives what are the edges in which 2 is participating, right? So Sir did mention about something called as adjacency matrix. So whatever we this is a graph that we are representing pictorially. But when it comes to representing graphs in mathematical and then mathematical notation and then computing stuffs out of it, we would rely upon something called as adjacency matrix and then adjacency list. Those are the most commonly used forms of storing a network. So adjacency matrix is nothing but a matrix wherein it has rows and columns. It's a square matrix. So it has rows and columns wherein both rows and columns are nodes. So let's just say we have 3 nodes forming a network, then it will be of a size 3 cross 3, wherein we'll have the rows will be 1, 2, 3, and then the columns will also have the same node 1, node 2, node 3. If there is an edge between node 1 and node 2, then the cell A, I, J, wherein I is 1 and then J is 2, will have 1. And rest of them, when there is no edge between particular nodes, then a pair of nodes, then we'll have 0. So that's a compact way of representing a graph. That's a better way of representing graph in mathematically and computationally. And then the other way is using adjacency list, which is just list of edges. They both have their own benefits and drawbacks. You'll get to know once you get started with doing some operations on top of them. So I'll not go into that. So what I wanted to cover here is there is a function called as ADJ. It just gives you an adjacent list of nodes, neighbors which are adjacent to a given node. So here the node is 1, and then it gives you all the neighbors who are adjacent to the nodes. So any doubts so far? Pretty simple, right? Straightforward. Yeah. And then NetworkX also has ways to remove stuffs from the nodes. So remove stuffs from the graph. So if you want to remove a node, dot remove node. If you want to remove a list of nodes, then remove nodes from, you give a list. Same way you can remove edges also. 1, 2, that will be the only edge which will be removed from your graph. And then if you want to remove a list of edges, then it's simply remove edges from, and then you give a list. Simple. Right. Yeah. And sir also briefly touched upon the notionality of having weighted networks. So weighted networks or network having properties and so on and so forth. NetworkX also has provisions to add these properties for at the node level, and then properties at the edge level also. So here you can say they have created different nodes. So node 1 and 2, and then they both have a property called as color, and then the color is yellow. And then the same way here they have created a edge called between node 1 and node 3, and then they are giving a property color, and then they are assigning it to blue, and then here an edge between 1 and 2 as a property color, and then it is red. So again, these are just simple things that we can add. And then weights also can be added in the form of in this following form, wherein you give a list of edges, and then usually to be source and target, or node 1 and node 2, and then you can pass in a third argument which is going to be considered as a weight of the edge. So here we have added weight 0.125, 0.75, and so on and so forth. Pretty simple. Yeah. And then you can do the same for the graph level also. We saw how we can add attributes at the node level, at the edge level, and then at the graph level also. Here there is a graph level attribute called as a day, and then you can add values there, and then you can change them also. Yeah. Node attributes, edge attributes, pretty similar. And then this is a little bit important for your hands-on session, because most of you are comfortable with linear algebra, I assume. And then how do we convert the graph that we see here into a adjacency matrix on which we can do some using which we can do some useful stuff. So in order to do that, there are multiple ways. As I said, the one simplest way is you call nx dot to numpy array, and then you pass in your graph object. Here our graph object is G, and then it gives you a numpy array. So from once you have a numpy array, I think whatever you know with NumPy, you can do that. So you would have known you would have used NumPy in your other courses or other projects. You can do the same with that, right? So I will also go over the NumPy quickly. Just this is not an full overview on NumPy. I just wanted to make sure everyone is on the same page so that you guys can comfortably work with it. So NumPy, how do we create a NumPy array? Just np.array, and then you given a list which will be converted into an array. It can also be a list of lists, wherein it will be a 2D. It can be 2D or n-dimensional arrays can also be created using this. And then here there are like other ways in which common ways which we will be using. So np.zeros, which creates this array of size 3, and all of them are zeros. So here it's a matrix of size 3 comma 3, and then all of them are zeros. And then this is a special kind of thing where it creates array with all the values 1, and then the shape is captured from another NumPy array object. So once like, and then it inherits the shape property from that object, and so on. Other ways to create all those things are there. I will leave it up to you guys to explore those things. And then some important things like how do you get, given an array, how do you get the minimum value that is stored in the array? How do we get the maximum value? Just simply np.max and then the array, and then np.min the array. And then the most important thing is sum. So here you can do np.sum, and then you pass in the array, compute the sum of all the values that are stored in the array. There are other ways in which you can specifically look at sum along the columns or sum along the rows. How do we use np.sum? So np.sum, and then you pass in the array, and then there is a property called as it's an argument called as access. If you give 0, then it will compute the sum along the column, and then if you give 1, it computes sum along the row. And then the other important things which we thought you guys will be using is something called as argmin. It returns the index of the largest value that is stored in the NumPy array. Do you have any question? Okay. Again, you can do the same thing for along the column wise and along the row wise and so on. And then there are like ways to check if there are any values that are of your interest. Say you want to find values which are greater than 10, you can do the same thing here. If you want to just check for any entry that is having a value 1, you just put np.any and then the array, and then it gives you true if there is any such value that is not 0, and then it gives you false if all the values are 0, and so on. Yeah. So this is the again, so this is a matrix, and then you can do all sort of things that we do in linear algebra. So the simplest thing is addition, subtraction. You just if you want to add two arrays, just array 1 plus array 2, array 1 minus array 2. And then if you want to do matrix multiplication, which you will be doing, I assume, for some of the questions. So just mat mul array 1 and array 2. So it does a matrix multiplication of arrays. Right. So with that, I think I've just given you a brief about NetworkX introduction. So now let's move on to the hands-on session. So same thing, we just open this collab, make a copy. We'll just wait for like 2 minutes, and then we can go over it. Yeah, just connect to this second collab, and we'll wait for like 2 minutes, and then we can get started. Are you guys able to connect? Anyone facing any issues? No? Okay. Shall we move forward? Okay. So what we have done, I mean, I assume you guys have created a copy of it, and you guys are able to edit it, because I haven't given the permission to edit, so you guys won't be able to edit it in this copy. So what we have done is we have taken a road network from Stanford repository, and then we are going to use that for our session here. So the first few cells till where you are able to see where you are able to plot the network are all boilerplate codes which we have added. So please do run till there, and let us know once you are able to let us know if you are able to run everything, and then you guys are ready to go. So yeah, just run those cells, and then yeah. Sorry? Sure. So yeah, just parallelly you guys run. Meanwhile I will just explain. Just a road network data set from Texas, TX. So here the nodes are different cities. Unfortunately, we don't have the names of the cities. They have given the cities as zeros and ones, 0, 1, 2, 3, an integer. So we don't know the city names, but it is from Texas. And then it's an undirected graph. So wherein there will be an edge between city 0 and city 1, which means there is a road connecting city 0 and city 1. So we'll explore this undirected graph for our work right now. Yeah. Yes. Sorry? QR code, yeah. Are you guys able to run till this plot? Most of you guys? Because we experienced some issue with getting the plotting. So, yeah. Cool. So again, so what we want to actually emphasize on here is like graph is another data structure wherein you can just ask. So we just ask a lot of questions in day-to-day life. You can do the same to a graph also. So we just want to cover that aspect in this tutorial. So if you are able to take away this ideology, that's more than enough for us. So with that, let's get started. So let's start with, we have framed it in about 14 questions, wherein first 10 are like pretty basic level question, and then which we will be covering, we are planning to cover in this session. There are like few questions which are kind of advanced, so you can take it to your home and then you can try to solve those things. So with that, we'll just start with the first question. So you guys are able to load the, so what we have done so far is we have created a network object called as mini road network. Instead of working with the entire road network, which we experience it to be pretty slow in Colab, so we are going with mini road network. So given this mini road network, we are going to ask the first question: how many cities are in your road network? So what is the answer for this? Number of nodes. Super. So you guys start coding. Maybe we'll wait for like a minute. You guys just do the coding, and then we'll do the same here. Yeah. So how do we get a node from a number of nodes from NetworkX object? So anyone able to solve it? Sorry? 3845. And what was the approach that you use? What code did you use?
I took the nodes, all the nodes, and take the length.
Okay, so that's good. So is there any other way that you can get the same from an adjacency matrix? How can you get from an adjacency matrix? Just a question. How do you? So it's an adjacency matrix. So I explain adjacency matrix. Size of the matrix. So it's like n cross n, node cross. So you can do that also. Okay. What about others? Others are able to get the list of nodes, like the size of the number of cities in this road network. Still working? You guys need more time? Okay. So let me do it in the adjacency form way. So adjacency is equal. Sorry? 3845. Cool. And what was the approach that you took? So list of nodes and then you found the length of the thing. So what was the command that you used? Just dot nodes, right? Dot? Mini road networks.
Converted the mini road network to list.
How did you do that? So here is one. So again, as we already have seen multiple ways to do it. So one way which we can also do is get the adjacency matrix, and then we can figure out the number of nodes, as adjacency matrix is a square matrix, and then the shape gives you the number of nodes. Again, adjacency matrix need not be always square. There are like some heterogeneous network also, wherein you have different sizes, different number of nodes, but we are not covering that here. So while it is running, let's go to the next question. So how many roads are there in your road network? So what is the answer for that? What would be the answer for that? What is the thing that we are looking here? Number of edges. So we also already defined this road network. Cities are nodes, and then the edges between them are the roads, right? So yeah, just code for getting the number of roads. You got it already? So what is it? Okay, dot edges. Okay, edges. So what does dot edges returns you? List of tuples. So what are the tuples actually? That two nodes that interact in a edge. So you get the list of edges and then you found the length. What about others? Others are able to do that? There is. Again, as I said, from the starting I'm saying, so NetworkX has like multiple ways to solve it. I just want to say some basic things or the things which I use. You guys are always free to dot number of edges, yes. So the third question, are there any roads that originate and ends in the same city? So what are we looking for here? Roads of length 0. Okay, so roads are edges. So uh, what do we mean by length of an edge being 0? Oh, a node which has 0 edges. So it means a city which has no road. But the question is, are there any roads that originate and end at the same city? What like again, what are we trying to see here? There is a road wherein it starts from city A and it ends at city A. No, not exactly. Okay, so maybe you guys are not aware of the technical term. So the technical term is called a self loop, wherein which is again it is some a network related technical term which you will be using. There are like some or there are like a lot of usefulness for this self loop thing. So there are like in biology, there are like certain proteins which the expression of certain proteins will actually inhibit its growth. Say for example, you can have in a given area, you can have like certain number of say predators only or certain number of deers only, because the population of it, if the more deers you have growing in the same area, then it requires a huge number of feet to be keep on growing with the same population, right? So if you increase the size, increase the number of deers, again the growth rate will decrease. So it kind of inhibits its own self. So we represent that as a self loop. Again in this question, are there any roads that originate and end at the same city? Now that we have understand this, how do we solve, like how do we answer this using adjacency matrix? Yes, exactly. So if I give you an adjacency matrix, you look at the diagonal, and then if the diagonals have 1, which means you can say there is a city X which has a road to itself, right? You can use again NumPy for solving this, and yeah, take your time, solve it, and we'll also see how we solve it. So if you guys are using, again, I mean, you guys have to use the same what I said. So there is in NumPy, there is a way to get the diagonals. So there's something called as np.diagonal, and then you can pass in the adjacency matrix, and then it gives you an array of elements in the diagonal elements. So yeah, use that functionality, and then figure out whether there is a city which has road to itself. Anyone completed with that? Generator of what are you?
Adjacency matrix.
Okay.
I gone through the diagram in a single row.
Uh,
Search for, I put a filter with the keyword.
if it is equal to 1, then do something. Or okay, again other way. 0, 0. And what was the approach that you took?
Equals to np.diagonal of adjacency.
np.diagonal of adjacents. Okay. p.any. So this is a function which returns true if the condition any one of the cell in the np array matches with the condition, and then it gives you false when none of those things matches a condition, and then we are going to give np dot null of what was the name of the adjacent adj. Yeah, so it's false, which means there is no such road that originates and ends at the same city. Now we'll go to the next question. So get the top 5 cities that are highly connected to other cities. So what does this mean? So let's just say you take India, then which are all these, which could be these cities that are like, that kind of, again, ignore the road connectivity. You can also think about connectivity in general. Which are the cities that will be highly connected to other cities? Wherein you go to a city and then you have like multiple options to go to another city of your choice. Super. So the nodes which are have more incoming and outgoing edges are, in a simpler term, a city which has lot of ways to go to other cities. So you have like railway connection to other cities, road connection to other cities, air through airport, and so on and so forth, right? So again, that's the correct question, the correct answer. And then how do we solve it? This is something called as, in network term, we refer to this notion of the number of edges that are originating or ending at a particular node, something called as degree. Okay, so what we are trying to ask is, can you find the top 5 nodes which has higher number of degrees? Okay, how can you do that? If I give you an adjacency matrix, how can you solve it? Yes, exactly. So if I give you an adjacency matrix, you sum along the row or column. Either way, it's same, and then you figure out the indices of the nodes which have the highest number of edges or degrees. Right? Yeah. Yeah. You guys take your time, solve it, and after a while, I will give you the code. Maybe we'll just start coding that. You guys can have a look at it. So what I want to do here is, first I want to get the names of the nodes first. Let's go. Yeah. So let's get names of nodes, which is equal to, okay. So So this is going to give me an array which has the names of the nodes which I require to print it. And then once I have the names, now I have to figure out the degree. So which is just sum of the adjacency matrix. So degree is equal to adjacency dot sum. Zero. Are you guys able to get till here? Get the degree? Yes? Or are you guys having difficulty with that? So you understand, right? How I get the degree? So just sum along either the column or row. Either way is fine for us, and then that gives us the number of degrees for a particular node. Now we have to, once we get the degree, now we have to retrieve what is the node name and then what is the degree. So I have a bit complicated way of doing that, but yeah, you can do it in a different way also. Okay. Yeah. So just to explain the fourth line, what we have done so far is we get the list of the nodes, and then we get the degrees of those nodes, and then we use something called as arg sort, which sorts the given array in ascending order, right? So how do we reverse a array? There's a fancy way to do that. So you just use double colon and then put -1. Then it kind of reverses your array. And then I'm picking the top 5 of them. The same thing I'm doing it for the degrees also. So these are the names of the city, and then these are all the degrees, right? Again, the question 5 is similar to that. You just have to find the top 5 cities which are least connected to other cities. So what is the answer? Least connected. I mean, I'm not expecting the names of the city. Actually, what is the... So those are the cities with least number of degrees. There are very few edges connecting from those cities. So it's pretty much the same, right? The same code. We just have to, without the reversing. Yeah. We'll do that. Just going to remove the reversing part. Yeah. So we have it. So these are the cities which has least number of connectivity to other cities. So the other question is, what is the average number of roads a city has in your road network? What is this? Sum of? How will that say per city? How will you call that as a average? So the question here is, what is the average number of roads a city has in your road network? So let's just say a degree. Huh.
already have the number of roads, the total number of HSC already is that,
Huh.
and you already have the number of cities. So from that, you could
So okay, the question here is like an edge is connecting city A and city B, and then here let's just assume this is your network. Then what you're saying is like 1 divided by 2, 1 edge divided by 2, right? But what is the sum of degrees of the edge? So you have city A has how many roads? City B has, so totally how many roads you have? 2 roads. So it should be 2 by 2, right? So how do we calculate this? Is average number of roads is nothing but average number of degrees per node. So you get the degree of each and every node, sum them up, and then you divide it by number of nodes. And so instead of dividing the number of edges by nodes, you are dividing sum of degrees by nodes. So that's a small change here. So others are able to follow that? Yeah. Now you have a list of degrees. So what do? Just sum the degree, sum of those, sum the degree and then divide it by number of nodes. Can you guys do that? Yeah. Same thing, I just did it with adjacency matrix. So I sum along the row, and then it's going to give me the degree for each and every nodes, and then I use mean to calculate the average of it, right? Yeah. So let's get to the interesting part. So Question 7. So find the shortest route between the highly connected city. You can take the first city name that you got, and then leastly connected city, which is the bottommost one which you got. So this is like a normal general question that we can ask, right? I want to go from A to B. What are all the stops I should take, right? So again, you can solve it with adjacency matrix also, but it kind of involves a lot of, playing around with matrix multiplication and so on. So here we will, from now on, we'll look at some of the inbuilt functions which are available in NetworkX. So there's a function called as shortest path, NX shortest path. Just Google about this, read about it, and then pass in the required parameters, and then let me know if you are able to get the shortest path between the highly connected city to least connected city. So are you guys able to land on the documentation for shortest path from NetworkX? Okay, maybe we'll do that. So let's Google shortest path. Shortest path. So this is the documentation, shortest path. Okay. So this is the definition of the arguments that we need to pass, parameters that we need to pass, right? So what does it say? There are like a lot of them are none, or some of them have already been populated with some values. We don't have to care about it. The first parameter is G, which is nothing but a network graph. So what is G in our case? Sorry? Mini road network is our thing. And then what is source and target? Start and end node. Yeah, just do the same. I think you will be able to get the path. So this is the path, right? Path starting from node city 535, and then ending at city 12,091, right? So these are all the different cities that you have to visit in order to move from a city which is highly connected to the city which is least connected. Yeah. I hope you guys are able to run this. Are you guys having, are you able to get this? Yep. Okay. Cool. So now let's move to the next question. Find the city that occurs most frequently in the shortest route between cities. By the way, yeah, so again, I just want to emphasize the fact that there could be multiple routes from source to target. You can have like different hops you can take between your source node and target node. What we looked at here is the shortest route, the route which has minimum number of nodes between them. Yeah.
Would we be able to plot this?
Yeah, I think you can plot it. We just have to get the subset subgraph of this node, and then you can do that. Yeah. Yes. So yeah, so we are looking at the shortest path, and then this question is kind of interesting, right? Find the city that occurs most frequently in the shortest route between two cities, or to be precise, it will be any two cities. So what are we looking at here? Firstly, why will this be somewhat important in the context of road network?
It's asking from to go from city A to city B. If we are passing through some other city.
Yes, exactly. And then that other city should be occurring in the shortest path of all other or many of the such shortest paths. Sorry? Yes. So some sort of centrality is coming into picture, right? So a city which is ideally, let's just say that again, it doesn't happen in that way, but it is in the it is a junction through which you have to, if you want to go from node A to node C, you can't ignore node X. Node X, you have to your shortest path should pass through node X. Then it means that node X has some sort of a centrality or some sort of importance that it dictates in the network, right? So it could be an important junction. Say in Chennai, Katipara is one such junction, wherein like roads from multiple sites, multiple other areas are being connected. So in order to given a road map of Chennai, how do you extract Katipara out of it? You can't. And let's just say I change the name from Katipara to 123. Just some random numbers I have given. How do you get an interesting junction like that? So this is a way in which you can do that. And then again, you can do it in mathematically also, but it will be time consuming. The technical notion of this is called as betweenness centrality, right? So if you run this command nx.betweenness centrality, again, go through the API documentation, it will give you the nodes, nodes and then the betweenness centrality of those nodes, and then you have to figure out the node which has the highest betweenness centrality. So it occurs between pairs of nodes. So that's what we are trying to solve here. Yeah. Any questions in the betweenness centrality concept? Okay. Yeah. Go through the API documentation and yeah. We'll just go through this betweenness centrality. the same thing, betweenness centrality, and here you don't need to specify any source and target as such. So it iteratively, it kind of enumerates over all the pairs of nodes in your network, and then it gives you the betweenness centrality for all the nodes. So I'm also not covering the formula, how do you calculate it, because again, it's an introductory course. You can feel free to go through this, how this betweenness centrality is calculated. So what is it? Meanwhile, when it is computing, it kind of it does take some time to compute. So what does this betweenness centrality does is it returns you a dictionary, wherein the keys of the dictionary will be the node name, and then the values will be the betweenness centrality that is the betweenness centrality of the node. And then I'm doing some Python way of just making it more readable. That's all I'm doing. So meanwhile, when it is being loaded, let's move to the ninth question. Find the busiest road in your network, the road which is part of most of the shortest route. So what is this actually? So we saw the we saw the city which is occurring more frequently in the shortest route. So let's call it as busiest city, and then now we are calling something called as busiest road. So what are we trying to find here? Similar to the previous one, right? A particular edge which is part of most of the shortest path. Let's just say a road connecting some important city and then another important city. Then whoever wants to go from, again, there will be a lot of traffics coming into the important city A, and then there will be a lot of traffics that will want to go from city A to city B, because city B is also equally important as city A, right? So generally the traffic in this particular road will be higher. So that's what you are trying to calculate. Again, the technical term for that is edge betweenness centrality. Again, betweenness centrality is for the nodes, and then we are looking the same for edge also. Yeah, so it's called as edge betweenness centrality. think we haven't updated this, right? Yeah. Find the largest set of I think we haven't updated this here. Okay, no problem. Yeah. So meanwhile, when we get answers for question 9 and 10, we look at the question 8 and 9. We look at the last question. So find the largest set of cities that are fully connected. That is, cities that have road with each other, between each other. So what are we trying to look here? We are trying to find some sort of a cluster or some sort of a group of cities from where you can go to other city with just a single road. You don't have to go through like multiple cities to reach a particular city. So there is this some special subset of cities or a group of cities wherein you can go from one city to other city in just one hop. So this set of nodes in a graph are called as something called as click, right? So let's just say you have a Facebook a network like this, and then you can find clicks as a group of tightly connected friends, wherein a group of friends who knows each other very well. So they are all friends of each other. You don't have to go from one. Yeah, so that's basically what a click is. Right. Again, in NetworkX, you can do it by something called as node click number, and then it gives you the number of the clicks which has the most number of nodes in it. So in this network, it happens to be only three. Like there is only three cities. There's only the maximum number of the size of the click is just three. There are like some random subsets of, not random, some subsets of nodes which are tightly connected, and then the number of them are 3, right? Yeah. So with that, we have covered the basic parts of what we wanted to cover in this NetworkX. Again, those things, okay, we got the answers also. So this is the city number 2148. Seems to be the city which is highly occurring in the shortest path in our network, and then the road connecting, of course, the 2148 is showing up here, the node 2148, city 2148 and 2150 seems to be the busiest road in our network, right? So with that, we have covered the basic things, and the advanced things we have given the hint also. You can look at it. We are also again, so these are like some higher level concepts in networks, and then what are the other ways in which we alter the network, and then we see properties. So the first one is something called as network perturbation. Again, I'm not going to cover these advanced concepts here. So perturbation, what is the meaning of perturbation is like you make some changes to your network or changes to the model that you are studying, and then you observe how it affects the model's performance or properties in a way. So in here, what we are asking here is delete the top 5 busiest roads in your network. So busiest roads are the roads with the highest betweenness. You take the top 5, delete them. So of course, there is a lot of traffic was expected to go through those roads, right? Some catastrophic event happened, and then those top 5 roads are no longer usable. Then what happens to your network? So one such property is called as diameter of a network. So diameter is nothing but the longest shortest path. So shortest path is the shortest path between node X and node Y, and then the longest shortest path is called as diameter of a network, which is similar to a diameter of a circle. So if you have a circle, you can draw a lot of chords, but if you have a circle, you can draw a lot of chords of different size. There is one chord which is the longest of among them, which is the diameter, right? So that's the property that we are looking to do here. So you have codes to delete edges, right, from the previous introduction collab, you can do the deletion and then figure out what is happening to the diameter of your network. So ideally, what should happen to this diameter? So you have somehow distracted the busiest road. What will happen? Or somehow deleted, diameter will shrink. Okay, then I just go ahead and destroy all the busiest road, right? My time to commute from IIT to home will shrink. It will increase, yeah. So the busiest road are ideally the most used road to go from one place to another, right? The more you cut down this busiest road, the diameter of your network increases. So it's a way of measuring how fast your network, a road network is being unusable, right? Yeah. And then the same thing here, instead of deleting the roads, we are deleting the junctions. So somehow some junctions of a city got affected, then what will happen? Again, here also, in theory, the diameter of your network will increase. So those are the main important junctions. So now you have to find an alternate route to go around those junctions. Right. So this is another thing, network is fragmented. So fragmented is, loosely speaking, your network splits into multiple pieces. So what we call in network theory, it's called as connected components, right? So there are like subsets of nodes which are connected, but there is no edge between subset 1. So there is no way to go from subset 1 to subset 2. They are all connected on their own, but there is no way to go from this cluster to this cluster. Those are all fragments, or you can call them as connected components. So if you delete the busiest road, are you seeing more number of fragments? Are your network is getting fragmented? You are not able to go from one node to another node. The same thing we do after deleting the cities also. Yeah, just try these things with your free time. Look for those keywords. Just Google NetworkX and then connected components, NetworkX and diameter, and I think there will be a lot of just one-liners will be there. You just have to use it and then. Yeah, so the networks which we got is from Stanford Large Network Dataset Collection. There are like other interesting networks also, like road network. We have like citations, air traffic, and so on and so forth. Feel free to explore those things. If you have any doubts, questions, or if you want to in some way understand more about networks, you can always reach out to Karthik sir. And yeah. So with that, I would like to conclude the NetworkX hands-on session. So I can take some questions if you guys have any questions related to this, whatever we saw now, or something else related to networks also. So are you guys able to understand all the concepts that we covered, or most of it, or how do you guys feel? Yeah, we're able to understand most. Okay, then, yeah, then thanks for attending the session.